Hey guys, this is Acids and Bases Part 3. In this section, we're going to take a look at pH and pOH. pH is something you're probably really familiar with. pOH may be a little bit less so, but here we're going to actually learn some of the math that goes with it. So to start with, we're going to talk about what happens with water. Even when water is completely neutral, pure, nothing in it, something kind of strange happens with water. So water actually self-ionizes. What that means is that it actually breaks apart and comes back together, and what happens is it forms ions in the meantime. We talked about how water is such a polar molecule, and because of that, part of that molecule is positive and part of it's negative. So when a hydrogen from another water roams by, it might be attracted to the negative end of the water, so much so that it might actually pop off and attach to the other water. What happens then is you end up with what's called a hydronium ion, the H3O plus, and then the other water molecule is left without a hydrogen, so it becomes a hydroxide ion. Kind of a strange thing, happens all the time. It doesn't happen a lot in magnitude. It's a very small amount, but it is constant. So here's a representation, a chemical equation that shows this happening. So this water is going to pick up a proton, and it's going to come from this other water. So that's the water coming from this original water. That hydrogen is going to pop off and come over onto this hydronium ion. So that's what's happening there. You can also see it. Sometimes they'll simplify that out and leave off one of the waters. So they'll get rid of one of these guys and they'll leave this guy as just hydrogen. You'll see both representations. Both of them actually should be reversible reactions. So they should actually both have a double arrow here because that's constantly happening in both directions. So that's called something called the ion product constant for water. At any given time, there's exactly this concentration of the hydronium ion and 1 times 10 to the negative 7th molar for the hydroxide ion. And if it's pure water, that's what it's going to be. Even though it's constantly happening and coming apart and going back together, you have this basic constant of 1 times 10 to the 7th molar concentration for each ion. So what happens is we end up with a mathematical constant, which is really important for understanding acids and bases. So that constant is called Kw. The K is something that if you take any more chemistry, you'll likely study equilibriums, and you'll learn a lot about that. So this is the equilibrium constant for water. So the big K is equilibrium constant. We won't do anything else with that term in this section, but you just think about it as the constant for water. So when you see the brackets here, the brackets mean concentration. So the equilibrium constant of water is the concentration of hydronium ions times hydroxide ions, and those two concentrations multiplied together always equal 1 times 10 to the negative 14th. Always, always. So that's a really useful thing again when we talk about acids. We can do a lot of calculations with that basic fact. So basically how it works is when those two concentrations are equal, you know that you're going to have something that's neutral. If you have a greater concentration of base, then it's going to be basic. Of the hydroxide ion tells you it's a base. And if you have a greater concentration of the hydronium ion, that tells you that the substance is acidic. So let's talk about the pH scale. This is something, again, that you've heard of a lot, but it's kind of a curious thing what it actually means. It's not something that you usually talk about where it comes from and what it means until you get into chemistry, even though you've studied it at different points in science. So I think most of you already know that it measures how acidic a substance is. And I think most of you know that it goes from 0 to 14, or at least you've heard that at some point. So on that scale, 0 means a very, very strong acid, and 14 means a very, very strong base. If something's at a 7, it's right in the middle, so it's neutral. So pure water should be a 7. Okay, so here's a couple examples with this scale, and as we look on here, so this is using molarity instead of just the pH. So if I look at the molarity, here I have a very concentrated amount of H plus compared to OH. Notice the OH, even though that concentration is small, never actually goes to zero. But if I look at the exponents here on my H plus, which is the same representation as if they had said hydronium ion. So this one does not include the water, the hydronium ion does. So notice the exponents here go from 0 to 14, just like the pH scale, and that's kind of where it comes from. The concentration of hydroxide goes the opposite direction, from 14 down to 0. A couple interesting things to point out here. You would think that your gastric juice would be very acidic, and you would be right. Lemon juice, pretty acidic. One that I think is kind of funny that I always like to point out is milk. I think most people, if you ask them, they would say milk is basic, but actually milk is just a little bit acidic, so that's kind of a surprise. And then you can see the other things. Milk of magnesia is what you take when you have a sore stomach. That's magnesium hydroxide. And then we have our strong bases that we've talked about before. Okay, so we're going to look at that scale then, and how you measure pH. So a couple ways that you can measure it. The easiest one is a pH meter. So you have this little stick that's electronic and you stick it in the solution and boom, you know the pH. We do have some of those at school, and they work with our LabQuest Pros, and we can get a reading on that directly. But you will often see the use of an indicator. If you've taken much biology, in a lot of labs, they use indicators. They do in chemistry as well, but a lot of you have seen them in biology as well. And so an indicator is something that you put in the solution, and when it hits a certain pH, it will change color. There's a couple natural indicators that I think are commonly used. They're kind of interesting. Red cabbage, if you ever tried to do kind of some home science stuff, red cabbage works really well from that. You basically boil it down and you get this really dark red concentration. You put a little bit of it in everything that you're testing, and then you put your new sample in. And the new sample, then the red cabbage will react to it and change colors. So it actually makes a pretty nice indicator. That's a really nice rainbow of colors that you get from this red cabbage pH chart. Another thing that's natural that responds to pH is hydrangeas, which is kind of interesting. So if you see the different colors in those, that could be where they get them from if they don't use dye, is by what kind of, how acidic the solution is that they put in with the flowers. So this is a chart of just different chemical indicators, and we have most of these in our chemical storage room. One thing I just want you to notice is that they're really only good for a fairly small range of pHs. So there's a reason that you don't just have one indicator and use it for everything. It depends on what the pH range is that your product is going to have, which chemical indicator is the most useful. One that you guys have probably seen a lot is phenolphthalein, or you've heard of that before. That's a super common chemical indicator. If you take AP chemistry, you'll definitely deal with that when you study titrations, and that's a part of acids and bases. So we're going to look at the math a little bit. How do you calculate pH? So I'm going to give you the equations, and some of you guys might notice right away, oh my gosh, there's a log. Don't worry. If you haven't had logarithms before, this is not a place to worry about it. This is a really simple calculation, and your calculator will do all the work. As you take more math, you'll learn more and more about logarithms and some of their applications. One place that's a good place to look at applications for logarithms would be like the Richter scale for earthquakes. So, on that scale, if you have an earthquake that's 5 on the Richter scale and one that's 6, that's actually a bigger range than just one. So the same thing happens here with pH. We saw those very large or small exponents, and what happens is that on the pH scale, there's an order of magnitude difference between the different numbers on the pH scale. That basically means, by order of magnitude, I mean a decimal place, and the log is how that works. Okay, so all you need to know is, if you want to calculate pH, you're going to put minus, and then there's a log button on your calculator right next to the 7. You just click it, and then you type in the concentration of the hydronium ion, and it gives you the pH. So you don't have to do anything with logarithms, no fancy math here. You just got to type it in. So this equation is actually the same equation. I just have it rearranged to calculate the hydronium ion. I probably should have flipped sides on this, and that would probably make more sense. But if I'm trying to calculate the hydronium ion, There's more than one way that you can do it. I think the simplest way for you guys who haven't had a lot of logs is just to take 10 on your calculator caret negative pH will give you the concentration of the hydronium ion. If you've had more math and you want to do it a different way, that's totally fine. Okay, so I have a couple quick examples for you. Number one, what's the pH of the solution if they give you the concentration of hydronium ions? So I'm just going to plug this in my little calculator. So I hit minus, I hit the log button, and then I type in the concentration. Make sure you're careful on putting the exponents in. Make sure you use the exponent button. Don't do 10 caret and all kinds of craziness that sometimes kids put in their calculator. So use the capital E button, that is shift comma, to do 2.5 shift comma, and then -3 will give you the right exponent way to insert it into your calculator. So I put that in my calculator, I find a pH of 2.6. You should be able to tell the reasonableness of your calculation here. Like if you're outside of 1 to 14 here, then you should be concerned that you have a mistake. So the second example I have here, what is the hydronium ion concentration of a solution with a pH of 8.62? So this is the other equation. Remember, they're actually the same equation, just rearranged, but I'm looking for the hydronium concentration, which is over here. So I'm going to take that 8.62, and I didn't rewrite it here in that form, but I'm going to solve this equation, same equation as here, I'm going to do 10 raised to the negative 8.62, and I put that in my calculator. Oh, I put it below. So 10 raised to the negative 8.62, and I get the hydronium concentration here. And again, that should fall in that range that was shown on the chart earlier for concentrations. If it's outside of that range, you know you have a problem. Okay, so the pOH scale. So we have the pH scale, which most of you guys had at least heard of before. The pOH scale is more specific to bases. So we're, instead of looking at the concentration of hydronium ions, and hydronium is what you focus on when you talk about acids, we're looking at the concentration of hydroxide ions. So it's the exact same thing, except the scale is flipped. And again, if you look back at the chart in your notes with the exponents, you can see that the exponents follow that pattern. So you have the exact same equations here that I showed you on the one before. So again, these two, same equation, rearranged for the other variable. And then this equation is new. When you get to use this equation, it's a happy time because it's really easy. The pH that we already talked about and the pOH, and these are all numbers between 0 and 14, if you add them up, they're going to be 14. So that's kind of nice. If you know one, you can do 14 minus that one and you get the other one. Handy little equation. So I have a couple example problems for you, and that's all we're going to do in this one. So a solution has a hydronium ion concentration of that. What is the pH of the solution? If you know the right equation, a lot of these things are just plug and chug. So I'm going to use the pH equation here, and I'm just going to put this concentration in for the hydronium ion. I plug that in my calculator, I get 8.3, okay? What is the pOH? Okay, now we just said that the pH and pOH together make 14. So that makes this a simple math problem, is I can take the 14 and subtract 8.3, and I'll get the pOH like that. What is the concentration of the hydroxide ions? Okay, when you get to like these multiple part questions, sometimes you get to the point where there's more than one way to do this. So I'm going to show you one way, and then I'll show you I guess I have both on there. So the blue way is one way to do it. The green way is a different way to do it. So the hydroxide ions, I'm going to use the equation from the last slide that said I can do that by doing 10 raised to the negative pH. So I do that with the 5.7, and I get this concentration here. The other way that you could do this is by using this equation I showed you earlier, that the product of the two concentrations has to equal 1 times 10 to the negative 14th. So if I take this guy and I divide out the 4.82 guy, I'm going to get that same answer. So again, more than one way to do these, especially when you've gone through a couple multiple parts and know a lot already about it. Is the solution acidic, basic, or neutral? We said the pH was 8.3, which is above 7, so I know it's basic. One more example problem here. So we have a solution with a pOH of 11.32. What's the concentration of hydroxide ions? So I'm going to use my hydroxide ion concentration equation. I'm going to take my 11.32 and put it in for pOH, and that gives it to me. So that's all you have to do on these. The equations, once you get to use them a couple times, they're really not too bad. Concentration of hydronium ions. So this is where, since we already know one concentration and I don't know, I could go ahead and solve for the pH first, but I just went ahead and did it this way, where I'm going to divide out the 4.8 that I had from above and put that in there. And when I do, I get my concentration in here. I could have done 14 minus 11.32, that's my pH, and then use my regular pH equation. Whichever one you feel like is easier is fine, you get the same answer. The last question, is this one acidic, basic, or neutral? So I'm going to say I have a pOH of 11.32. That's really high. So if I have a high pOH, I know my pH is actually really low because it'd be 14 minus this. So if I went ahead and did that beneath, that would be 2.68, which is a very low pH, so it's definitely acidic. So that's the math with acids and bases, probably the last math that we actually have for the whole year. So we're going to practice some of that calculating and see how it goes.